Okay. So now we've talked about that. We've got to talk about elastic potential energy. So we sort of implied, we said, it's a fact, that mechanical energy is really just kinetic plus gravitational potential. But to do homework problems and make them more interesting, we also throw in springs. Right? Springs have their own potential energy. Technically, it's not part of the classical mechanical kinetic or mechanical potential, but it's easy to throw it in, and the concepts are all the same. I was going to do it, slow and in detail, but since we blew so much time at the beginning, how about we just get the formula? I can't tell if that was popular or not. Let's see. And popularity is all that is important here. Okay, so the mass here. So say we have a spring at some natural length. We'll call that the origin. Right? So there's like L naught. That's the length the spring wants to be. Oh, I sound like a biochemist giving it some will or something. That's the length the spring wants to be. Now it's going to go interact with the mass. So we're going to push along the x direction, right? Like that. And so let's just do a little mini version. The mass pushes, again, anthropomorphic, pushes against the spring. I'll devolve into sports analogies in a minute. Therefore, this is my dramatic reading. It has the potential to bounce back. Okay, if we're letting it have consciousness and muscles, we could say it could go here. Now I've built up potential energy in the spring, so I could get pushed back and gain it back as kinetic. So it's just like the gravitational potential. When you move something up on that bar, it has the potential to fall down and gain a bunch of kinetic energy. So exact same idea. So you just have to say the potential energy of the spring equals the work to compress the spring, to compress or push something against the spring. All right, so it's equal to, we have to do the integral, because this work is a case where a force is changing, right? As we push against a spring, the force changes. This is pretty much the only changing force in integral we can do. So unfortunately, we can't make up a bunch of other ones. Well, we could, but it's the integral then. If you go from the origin to some compression x, what is the force? Well, let's see. So we're compressing the spring, so the mass is pushing on the spring. So we put kx, right? It's not negative kx, it's just kx, because we're the force on the spring. We think of the spring as the system. Or if we wanted to think it's the mass spring system, what force do we have to push? We push forward, right? It's not the spring's force back on the mass. It's what we're pushing the system with. So forward, the external force. So kx and then dx. That's all it is. Integral of kx dx over from 0 to x. From 0 to some position x. I should be labeling things x prime. I'm irresponsible. I'm not going to. There we go. That's equal to 1/2 kx squared evaluated from 0 to x, which is equal to 1/2 kx squared, which is the potential energy of a spring. Okay? So if you compress it at distance x, it's 1/2 kx squared. That's assuming it's 0 when it's uncompressed. Okay? Assuming us equals 0 at x equals 0. If you get creative and make u of the spring some finite value when it's not at 0, one, that's really stupid, but it'll throw that formula off. Okay, so always the energy of the spring really is 0 when it's uncompressed, because that's when it can't push anything. So it's really not as arbitrary as the gravitational case when you can always go down lower to the basement. Why is a potential energy equal to work? Because remember, work transfers energy from kinetic to potential. So we did the work kinetic energy theorem. You could sort of also do a work potential energy theorem. You could say the work you do increases the potential energy. It's just usually we skip that and go straight to what you'll hear about Tuesday, when you have a total system with a potential energy, with a conservation of energy. But yeah, but it's the same idea. If you do work on it, you're increasing its potential energy. Just like when you lift it, you're doing work on it. Anyway, I just want you to have that formula so that we can now do the problems. Okay, so 1/2 kx squared, you may have heard that before if you've had physics before. But that's where it comes from. Just a quick integral.